Right now, somewhere above your head, a giant white rock is quietly getting smaller and nobody on the ground can feel it happen. That rock is the moon, the one you have looked at your whole life without ever once suspecting it was in trouble. It is not exploding and it is not falling. But new measurements show it is shrinking in a way that could shake the exact ground future astronauts plan to walk on, which changes what this story means for anyone hoping to go back there. Before we get into what NASA actually found, stick around and hit that subscribe button because this channel exists to hand you the moment scientists change their minds about something they thought they understood. Picture the surface the way an old apple looks after it sits on the counter for a few weeks. The skin does not explode, it does not crack all at once, it just slowly wrinkles because the inside is shrinking a little faster than the outside can keep up with. That is roughly what is happening to the moon, except the moon is not made of apple flesh, it is made of rock. And it has been doing this quiet wrinkling act for a very, very long time. We are not talking about the moon vanishing or turning into space dust. We are talking about a slow, steady tightening, the kind of thing you would only notice if you had incredibly precise cameras, incredibly patient scientists, and about 50 years of old data nobody had fully understood until now. That is exactly what happened. And once you hear how they figured it out, you will never look at a full moon the same way again. Think about how still the moon looks tonight, if you happen to catch it. No clouds drifting past it, no storm swirling across its face, just a fixed silvery coin hanging in the dark, exactly where it was last night, and the night before that, and every night of your entire life. That stillness is not a lie, but it is not the whole truth either. It is the kind of stillness a glacier has, or a mountain range has, something that looks frozen in a single glance but is actually moving on a clock so slow that a human lifetime barely registers as a tick. Let us pull back now, because the shrinking moon story does not start with a satellite. It starts with something almost everyone believes about the moon without ever questioning it. Most people picture the moon as a dead, frozen, unchanging rock, a leftover chunk of space debris that has looked exactly the same since it formed and will look exactly the same forever. And that belief feels obvious. It feels safe. And for most of history, nobody had a reason to doubt it. The moon formed a long time ago, more than 4.5 billion years back, in an event so violent it is almost hard to picture. Most scientists believe a planet roughly the size of Mars, sometimes nicknamed Theia, slammed into the young Earth. That collision blasted a huge amount of melted rock and debris out into space. Over time, gravity pulled that debris together into a ball, and that ball became the moon. Try to imagine that moment for a second. Not a gentle nudge, not a graze, but a full planet-sized object crashing into another planet-sized object, hard enough to melt rock into glowing liquid and fling it out past the sky. The moon you see tonight was born out of that violence, cooling and hardening over millions of years into the pale, quiet shape we recognize today. For a long time, people assumed that once the moon cooled down from that collision, it basically stopped changing. It has no wind, it has no rain, it has no rivers or oceans grinding down its rocks the way Earth's surface gets constantly reshaped. So the assumption made sense on the surface, no pun intended. If nothing is eroding it, and nothing is crashing into it very often anymore, why would it be doing anything at all? Here's the part most people never think about. The moon is not just a cold rock sitting still in space. It has layers, just like Earth does. There's a crust on the outside, the part we actually see and photograph. Underneath that is a mantle, a thick layer of rock. And at the very center, there is a core, similar to Earth's core, though much smaller. That core used to be hot, really hot. Billions of years ago, the moon likely had a partially molten interior, meaning parts of it were soft and liquid, almost like thick caramel instead of solid rock. Over billions of years, that heat has been slowly leaking out into space, because unlike Earth, the moon does not have a thick atmosphere acting like a blanket to trap the warmth in. As the inside of the moon cools down, it does what most materials do when they cool. It contracts, it shrinks, just a little, just a tiny amount over an unbelievably long stretch of time. But because the moon's crust is brittle and rigid, like a dry cracker instead of soft clay, it cannot smoothly shrink along with the interior. Instead, the crust has to buckle, fold, and crack to keep up. Think about what happens when you let a grape sit out for a couple of weeks until it turns into a raisin. The inside loses volume, but the skin cannot shrink smoothly along with it, so it wrinkles and puckers instead. Scientists sometimes reach for that exact comparison when they talk about the moon, because the physics, on a much larger and much slower scale, is not all that different. For decades, this idea sat quietly in scientific papers, mostly ignored by the public. Researchers studying the Apollo missions from the 1960s and 1970s had noticed strange features on the lunar surface. Long, cliff-like ridges called scarps, some just a few dozen feet tall, running for miles across the ground like stretch marks on a giant gray balloon. At the time, most scientists figured these scarps were old news, leftovers from something that happened hundreds of millions or even billions of years ago, back when the moon was still cooling from its early, hotter days. The general belief was simple. The moon shrank a long time ago. It finished shrinking a long time ago. Whatever wrinkles it has, it earned early, and it has been sitting still ever since, just like everyone always assumed. That belief held for a long time, because there was no easy way to check it. You cannot exactly send a tape measure to the moon and measure it every year. You need incredibly precise photographs taken from the exact same angle, years apart, comparing every ridge and crater down to details smaller than a school bus. For most of history, that kind of comparison simply was not possible. Back during the original Apollo era, the cameras astronauts carried were good for their time, but nowhere near sharp enough to catch changes measured in feet or inches across a landscape that spans thousands of miles. Photographs taken years apart were often shot from different angles, different lighting conditions, different sun positions, which made careful comparison almost impossible. Scientists were essentially trying to spot a hairline crack using a photograph taken from a moving car. Then came a spacecraft that changed everything, a robotic orbiter launched by NASA in 2009 called the Lunar Reconnaissance Orbiter, or LRO for short. Think of it as a security camera that has been silently circling the moon for well over a decade, snapping incredibly detailed photographs of the same locations again and again, year after year, patiently building the most complete photographic record of the lunar surface ever created. Researchers began feeding those thousands upon thousands of images into careful comparisons, looking for anything that had shifted, even slightly, from one pass to the next. This was slow, painstaking work, the kind that does not make headlines while it is happening. Nobody expected fireworks. Everyone assumed they would mostly be confirming what was already believed, that the wrinkles were old, finished, and frozen in time. Imagine the sheer patience this required. Scientists lining up two photographs of the exact same patch of gray dust, taken years apart, adjusting for shadows, adjusting for the angle of sunlight, checking boulder by boulder to see if anything had nudged even a few feet out of place. It is the kind of work that rewards obsession, the kind of work almost nobody outside the field ever hears about, right up until it produces an answer nobody expected. By this point, the picture in most people's heads, and honestly in a lot of scientists' heads too, was fully set. The moon shrank billions of years ago while it cooled from its hot, freshly formed state. It left behind these cliff-like scars as proof, and since then, it has been sitting quietly, finished, unchanging, exactly the still and silent object it appears to be every night in the sky. But that picture is about to change, and not in a small way. When researchers started overlaying the newest, sharpest LRO images against older data, and even against seismic readings left behind by the Apollo astronauts, patterns started showing up that did not fit the old story. Something happened that the textbooks had not fully prepared anyone for, and it centers on one of the most important regions on the entire moon. If you have ever paused a video like this to think back on a moment when something you always assumed turned out to be wrong, drop a comment describing exactly what cracked that assumption open for you, because comments like that are literally how we choose which stories to dig into next. The region in question is the lunar South Pole, and if that name sounds familiar, it should, because it is the exact area NASA has picked as the primary landing zone for the Artemis missions, the ones meant to put astronauts back on the moon for the first time since 1972. That is not a coincidence this story matters. That is the whole reason this story matters right now. In 2019, a team led by planetary scientist Thomas Waters at the Smithsonian Institution's National Air and Space Museum, working alongside researchers, including Nicholas Schmerer at the University of Maryland, published a study in the journal Planetary Science Journal that looked specifically at these scarps, those cliff-like wrinkles, clustered near the South Pole region. The expectation, based on the old assumption, was that these scarps should look like ancient, worn-down features, the kind that stopped forming a long time ago and have just been sitting there quietly ever since, slowly getting sandblasted by space dust and tiny meteorite impacts over billions of years. What the team actually found was strikingly different. Many of these scarps looked fresh, sharp edges, crisp lines, boulders sitting right at the base of the cliffs instead of scattered and worn away like they should be after ages of exposure. It is the geological equivalent of finding tire tracks in fresh mud instead of a cracked, sun-baked driveway. Something had shaped this ground recently, at least recently in terms of the moon's multi-billion-year lifetime. Picture standing at the base of one of these cliffs yourself, boots sinking slightly into gray dust that has not been touched by wind or rain for eons. Above you, a ridge of broken rock rises sharply, its edges still angular instead of rounded off, its shadow falling clean and sharp instead of soft and blurred the way ancient, worn features usually look. That sharpness is exactly what made scientists sit up and pay closer attention. Then researchers went back even further, pulling out old data most people had forgotten about. Seismic readings recorded by instruments the Apollo astronauts placed on the lunar surface back between 1969 and 1977. Those instruments, essentially the moon's version of earthquake detectors, had picked up dozens of moonquakes over the years, tremors shaking through the ground, and one of the strongest recorded quakes traced back to a location extremely close to these same fresh-looking scarps. Soon after connecting these two pieces, the picture completely flipped. This was not simply old evidence of ancient shrinking. This looked like evidence of shrinking that is still actively happening, meaning the moon may still be quietly contracting today, and that contraction may still be triggering real moonquakes strong enough to shake the ground beneath future footprints. Let us pause on the actual math here, because the numbers matter and they are wilder than you might expect. Researchers estimate the moon's overall circumference, the distance around its widest point, has shrunk by roughly 150 feet total over the last several hundred million years. To put that size in perspective, that is shorter than a football field, spread out across the entire outer edge of an object more than 2,000 miles wide. That might sound tiny, and honestly it is tiny compared to the size of the moon itself. But here's the domestic comparison that makes it click. Imagine a basketball slowly losing air so gradually you would need incredibly sensitive tools to detect it. Yet somehow that tiny pressure loss is still strong enough to crack the outer layer of paint into jagged little canyons. That is the scale mismatch scientists are dealing with. Small shrinkage, big surface consequences. Now flip back to the human scale for a moment. A basketball losing a whisper of air sitting on a shelf in your garage would never crack its own paint job because the material is soft and flexible. But swap that soft rubber skin for something brittle, something more like a dried out eggshell stretched over the ball. And now that same tiny loss of air is enough to send hairline fractures spidering across the entire surface. That brittle eggshell is basically what the moon's crust is behaving like. In parallel with the scarp research, other teams began modeling how these moonquakes actually behave. Because a moonquake is not exactly like an earthquake here on Earth. Earth's crust is soft and layered with water, which tends to dampen shaking fairly quickly. The moon's crust is dry, rigid, and brittle almost all the way through, which means vibrations from a moonquake can travel farther and last significantly longer than a similar-sized earthquake would here at home. A relatively modest moonquake on Earth might rattle windows for a few seconds and be forgotten by lunch. On the moon, a similar quake can keep shaking the ground for 10, 20, even 30 minutes straight, because there's nothing to absorb and dampen the energy the way water and soft soil do on Earth. That is an enormous difference when you're talking about equipment, habitats, or astronauts standing on that ground. Think about how unsettling that would actually feel in person. On Earth, when the shaking from an earthquake finally stops, it stops because the ground itself is soaking up the leftover energy, the way a wet towel soaks up water. On the moon, with no moisture and no soft soil layers to do that job, the vibrations just keep bouncing back and forth through solid rock, like a bell that keeps ringing long after you have stopped tapping it. This is also the point in the story where honesty matters more than a clean narrative. Not every scientist studying this data agrees on exactly how active the shrinking currently is, or precisely how often significant moonquakes strike near the South Pole region. Some researchers argue the fresh-looking scarps could partly reflect slower, more sporadic activity rather than constant ongoing shaking. The truth is, nobody has a live seismic network up there right now feeding back real-time data, so a lot of this picture is built from limited historical Apollo instruments and careful geological detective work, rather than a full modern monitoring system. That gap in certainty is not a weakness in the story, it is actually the whole reason this research area is exploding with new attention. Scientists genuinely want more information, and that desire directly shaped several of the newest missions being planned. Around 2023, additional analysis using AI-assisted pattern recognition on the full LRO photo archive helped researchers identify even more of these young-looking fault scarps scattered across the lunar surface, not just clustered at the South Pole, but showing up in patterns nobody had mapped out completely before. That kind of computer-assisted search matters more than it might sound like at first. A human researcher scanning image after image can only cover so much ground before fatigue sets in and small details start slipping past. Feeding the entire photographic archive into pattern recognition software let scientists check formations across the whole moon at a scale no team of people could manage by eye alone, and it kept turning up scarps that earlier passes had simply missed. Then, building on that momentum, a 2024 modeling study looked specifically at how strongly the ground might shake near candidate Artemis landing zones if a moonquake struck along one of these nearby faults. The results suggested that certain areas near the South Pole could experience meaningful ground shaking strong enough to matter for engineers designing landing pads, habitats, and long-term structures meant to survive months or years of use rather than a brief multi-day visit like the original Apollo missions. Zoom back out for a second and hold both scales in your head at once. On the cosmic scale, you have a 2,000-mile wide rock slowly losing internal heat that formed over 4.5 billion years ago during a planet-sized collision. On the domestic scale, you have engineers on Earth right now, in offices, running structural calculations, trying to decide exactly how thick a landing pad needs to be, so a future moon base does not develop cracks the way an old sidewalk does after one too many freezes and thaws. That is what makes this story different from a typical space headline. This is not simply an interesting fact about a rock in the sky. It directly connects to hardware currently being designed, budgets currently being debated, and mission timelines currently being adjusted. The moon's slow, quiet shrinking has moved from being a curious, historical footnote to being an active engineering variable in humanity's return to the lunar surface. And here is where this stops being about one photograph, or one cliff-shaped scar in the dirt, and starts being about us, about how confidently we plan to live somewhere we still do not fully understand. If the moon can still surprise scientists after more than 60 years of close study, it is worth asking what else we might be underestimating, simply because something looks calm and unchanging from 250,000 miles away. If any part of this story genuinely surprised you, send it to the one person in your life who confidently insists the moon is just a boring, dead rock, because watching someone's expression change mid-video is honestly one of the best parts of sharing science with people you actually know. So what happens next? NASA's Artemis program, managed out of the agency's Johnson Space Center, is specifically targeting the lunar South Pole region for its crewed landings, currently planned in phases through the later 2020s, precisely because that area holds something incredibly valuable: permanently shadowed craters that likely contain frozen water ice, a resource future astronauts could eventually use for drinking water, breathable oxygen, and even rocket fuel. That means the exact region getting the most attention for these newly discovered active fault scarps is the exact region where NASA wants to build long-term infrastructure. Engineers cannot simply pick a landing site because it looks flat and pretty in a photograph anymore. They now have to factor in seismic risk, the same way engineers on Earth study fault lines before approving construction near cities like Los Angeles or Tokyo. Picture a mission planner sitting in a conference room, staring at a short list of candidate landing sites, and realizing that a spot that looked perfect a few years ago now has to be weighed against a freshly discovered fault line running underneath it. That is not a hypothetical scene. That is roughly what has actually been happening inside planning teams as this scarp research has matured. To get better answers, researchers are pushing for something the moon has never really had before: a dedicated modern seismic network, a set of sensitive ground-based instruments specifically placed to listen for moonquakes continuously, rather than relying on decades-old Apollo data that was recorded using equipment that shut down back in 1977. NASA has floated concepts for exactly this kind of geophysical network as part of longer-term Artemis-era science payloads, though, as of 2026, full funding and a specific launch date for a comprehensive network have not been finalized. There's also a very human question sitting underneath all this engineering talk, and it deserves a moment of its own. If astronauts do end up living on the moon for extended stretches, weeks or months at a time inside a habitat, what does it actually feel like to experience a moonquake that can rumble on for 20 or 30 minutes? Unlike Earth, there is no wind, no rustling trees, no distant traffic noise to provide any kind of familiar reference point. Just profound silence, then a slow, sustained shudder moving through the structure around you, then silence again. Try to sit with that image for a moment. You are inside a small metal and composite habitat, hundreds of thousands of miles from home, and the ground beneath your boots starts to tremble, not for a few startling seconds like an earthquake back home, but for 20 full minutes, with nothing outside to explain the sound or the motion except the quiet, patient shrinking of the world you are standing on. Engineers designing lunar habitats are already thinking about this, incorporating flexible joints and shock-absorbing materials into early habitat concepts, drawing lessons from earthquake-resistant building techniques used right here on Earth in places like California and Japan. In a strange way, some of the safety knowledge humans developed dealing with earthquakes on our home planet may end up directly protecting the first long-term residents of another world entirely. Meanwhile, scientific interest in this shrinking moon story keeps expanding well beyond just the South Pole. Researchers are now re-examining old scarp data across the moon's near side and far side, looking for a fuller global pattern rather than just the cluster originally studied back in 2019. Some early findings, still being debated and refined as of 2025 and 2026, suggest similar young-looking fault scarps might exist scattered across multiple regions, hinting that this slow contraction could be a genuinely global process, rather than something isolated to one unlucky patch of terrain near the pole. As the picture sharpens, the numbers keep getting more specific too. Where researchers once spoke broadly about scarps forming sometime within the last billion years, refined age-dating techniques using crater counting, essentially estimating a surface's age by counting how many tiny meteorite impact craters have accumulated on top of it, now push some individual scarps to potentially less than 50 million years old, and in a handful of specific cases, potentially far younger still, geologically speaking, practically brand new. That kind of increasing precision matters enormously for mission planners working on tight schedules. A crewed Artemis surface mission currently targeted for the back half of this decade cannot simply operate on rough estimates measured in hundreds of millions of years. Engineers need numbers specific enough to inform real decisions. Decisions about exactly where to place a habitat, exactly how deep to anchor a structure's foundation, and exactly how much flexibility to build into life support systems that absolutely cannot afford to crack under stress. Every extra decimal point of precision that scientists manage to pin down translates directly into fewer unknowns for the people actually designing hardware. A landing pad engineer does not need a poetic description of an ancient, slowly cooling world. They need a number, a specific expected shaking intensity, a specific expected frequency of tremors, something they can plug directly into a stress calculation before a single support beam gets welded together. Somewhere out there, right now, a spacecraft is still quietly circling the moon, still snapping pictures, still adding to that patient photographic record that started back in 2009 and keeps growing sharper with every single orbit. Somewhere in a lab on Earth, a researcher is comparing this month's freshest images against ones taken years earlier, hunting for the faintest hint of movement along a fault line nobody had mapped a decade ago. Because that is genuinely how a discovery like this keeps unfolding, one careful comparison at a time. Somewhere else entirely, a mission planner is updating a spreadsheet, adjusting risk estimates for a landing zone based on data that did not even exist a few years back, quietly reshaping decisions that will eventually put real boots on real lunar soil. The story of the shrinking moon is not finished. It is still being written in real time, frame by frame, orbit by orbit, and the next major update could come from a mission that has not even launched yet. Picture one single number carrying the weight of this entire story, 150 feet. That is roughly how much smaller around the moon has become over hundreds of millions of years, a distance you could walk in under a minute here on Earth, yet strong enough, patient enough, and persistent enough to still be cracking open the ground beneath a mission humanity is actively preparing to fly. Bookmark this video or save it somewhere. You will actually find it again, because when Artemis astronauts finally do step onto that South Pole soil in the coming years, you're going to want to remember exactly why the ground beneath their boots is not nearly as still and silent as it looks from here. The moon has been changing this entire time, quietly, patiently, one imperceptible contraction at a time, long before anyone on Earth thought to look closely enough to notice. And now that we finally are looking, really looking, with better cameras, sharper instruments, and old data given a second chance, the moon is finally starting to tell us the truth about itself, one fresh crack in the ground at a time.